All right, so what I'd like to do today is to continue going over integrals involving trig functions, and in particular, I want to start looking at integrals that involve secant and tangent. Now, it turns out that the integrals that involve secant and tangent, they're actually very similar to integrals that involve cosecant and cotangent. So once you see how to do one of them, hopefully it will give you an idea of how to do the other. Now, some of the most useful identities, or probably the most useful identity that we want to remember when dealing with secants and tangents in the integral, is the Pythagorean identity for tangent and secant. So remember, you can turn the Pythagorean identity into tangent squared theta plus 1 equals secant squared theta. Okay, I need to just start getting rid of pens that are non-operational around here. So this is going to be one of our really important identities that we use repeatedly when we work with this kind of thing. The other thing that we want to remember is the derivative of tangent theta is actually secant squared theta. And the derivative of secant, whoops, that's a d by dx. I meant to do a d by d theta. D by d theta of secant theta. Does anybody happen to remember this one? I'll give you a second to kind of think about what it's equal to. Well, this one is actually equal to secant times tangent. Now, what does this mean? Well, this means that there are two u substitutions that we can try to use. We can try to use a substitution of a u equals tangent theta if we can then get everything written in terms of tangents of theta, and we can peel off a secant squared theta d theta. And we'll take a look at an example of what I'm talking about here in a minute. The other kind of substitution we can try to do is a u equals secant theta if we can make our d theta into secant theta tangent theta. So what are the circumstances under which we're going to be able to make those substitutions? Well, if I have something that looks like the integral of secant to the m theta, tangent to the n theta d theta, I will be able to, if m is even, then what I can do is I can rewrite this entire thing in terms of tangent theta except for a secant squared. So I can rewrite this as the integral of something involving tan theta times secant squared theta d theta. And then what do I do? Well, then I make a u substitution of u equals tangent theta, because then du is secant squared theta d theta, and I can do this integral, because now it just involves tangents, so my u substitution is going to work out here. So that's what I can do if I have even powers of secant. On the other hand, if I have odd powers on each of them, then what I can do is I can peel off a secant theta tangent theta, and then I will be able to do a u substitution of secant theta, because I can rewrite everything except for one secant theta tangent theta in terms of secant theta. Once I peel off a secant theta tangent theta, everything else is going to be, actually this will work not just with m and n odd, this will work with n odd in general. I can do this because then I peel off a tangent theta and one of the secant thetas. I rewrite all of the remaining tangents in terms of secants using the Pythagorean theorem, and then I use this substitution. There will be a secant theta tangent theta left over for me to work with. So let's take a look at some actual examples of this, because I think it becomes much clearer what I'm actually talking about here. when we see these kinds of things. So let's suppose that I want to do the integral of secant to the 9th theta times tangent. Let's say that we want to do this to the 5th theta d theta. So here's what I'm going to do. I'm going to rewrite this expression inside the integral as the integral of secant to the 8th theta tangent to the 4th theta times secant theta tangent theta d theta. In other words, I'm going to peel off a secant and a tangent. And now what I can do is I can say, well, this is actually the integral of secant to the 8th theta times 1 plus tangent squared theta squared secant theta tangent theta d theta. But 1 plus, I didn't do that substitution correctly at all, did I? Tangent squared is secant squared minus 1. So I meant to put a secant squared theta minus 1 in there. I'm glad that I was sort of paying attention, even though I obviously wasn't paying attention the first time I wrote that down. So now everything is secants except for this tangent theta at the end. But that's okay because I have a secant theta with it. So now what I can do is I can say, let's let u be equal to secant theta. Then du is going to be secant theta tangent theta d theta. So what I have here is a du, and everything else is written in terms of secants, which are my u. So once again, the hunt for a better pen. Let me go back up to the top here. So keep in mind what we're actually integrating, but I'm going to do this integral at the top here because I don't have a lot of space. So we've gotten it written down into this form. Now, this is going to become the integral of u to the 8th times u squared minus 1 squared du. And this is a reasonably simple polynomial antiderivative that we're working with here. So I can expand this into the integral of u to the 8th times u to the 4th minus 2 u squared plus 1 du. This is going to become the integral of u to the 12 minus 2 u to the 10 plus u to the 8th du. And once again, running out of room here on my tiny little whiteboard. So give me some space. Keep everything here in your notes. This is then going to become u to the 13 over 13 minus 2u to the 11 over 11 plus u to the 9 over 9 plus k. And then I just have to rewrite this thing in terms of my secants, right? So I need to take u's and replace them with secant theta. So this is going to become secant to the 13th theta over 13 minus 2 secant to the 11 theta over 11 plus secant to the 9 theta over 9 plus a constant of integration. So there we go. We've got that one worked out. What we don't have is still a pen that I like. That one's even worse. All right, all of these are going away. Maybe one in this box is going to be a little bit better. There we go. That one seems reasonable. All right, so hopefully everybody's okay with that example. Let's work through another example where we see how a different kind of substitution is going to play a role for us instead. So this time, let's consider the integral of secant to the 4th theta tangent to the 6th theta d theta. This time, we cannot do what we did the last time. The reason is because if I were to try to peel off a secant theta times tangent theta, I would be left with an odd power of tangent. And I cannot express an odd power of tangent in terms of secants, at least not without involving square roots. And I don't want to do that. That would not really help me, honestly. In fact, that would really screw things up pretty badly. So we don't want to do that. But here is what we can do instead. We can notice that we have an even power of secant. So I can actually think of this as the integral of secant squared theta tangent to the 6th theta secant squared theta d theta. In other words, I take one of my secant squareds and I put it together with my d theta. And now what I can do is I can rewrite this entire thing in terms of tangents, except for this secant squared theta d theta. So this is actually 1 plus tan squared theta, tan to the 6th theta, secant squared theta d theta. Why do I want to do it this way? Well, the reason is because now I can say, let's let u be equal to tangent theta. Then du is secant squared theta d theta. So that's nice because this is now actually my du. And that means I can turn this into the integral of 1 plus u squared u to the 6th du. Unfortunately, I'm now out of space. So keep in mind that this is the problem we're doing. We're going to go back up to the top and keep working this thing. So I turn this into the integral of u to the 6th plus u to the 8th du. That's going to be u to the 7th over 7 plus u to the 9 over 9 plus a constant. If I replace the u's with tangents, this is going to become tangent to the 7th theta over 7 plus tangent to the 9th theta over 9 plus a constant. And there we go. So this shows us sort of the two types of substitutions that make these secant tangent problems work out sort of nicely for us. The two substitutions to keep in mind are, you see if you can write everything in terms of secants, except for a secant and a tangent, and then you do u equals secant theta, because then the du gives you your secant tangent. That was our first example. In this second example, we saw that we were able to rewrite everything in terms of tangents except for one of the secant squareds, and then we can do the substitution of tangent theta because du then becomes secant squared d theta. Okay, so that makes this substitution work out. So you want to try starting by checking to see if one of those will work. Now the problem is that this isn't always going to take care of every single problem that you have. So for example, if I wanted to do, say, just an integral involving a tangent with no secants, and I'm just going to write this in terms of x. What if I wanted to do the integral of tangent x dx? In fact, I'm posing you a challenge here. Pause the video for a minute and see if you can think of a way to do this. All right, were we able to come up with something? Well, in this case, the trick that I'm going to use is I'm going to remember this is really the integral of sine x over cosine x dx. And I'm going to make the u substitution of cosine x, which means that du is negative sine x dx. And then this integral is going to be the integral of negative 1 over u du. And this is going to become minus log absolute value u plus a constant. So this is minus log absolute value cosine x plus a constant. In fact, we can go a little bit further here if we want to. We could remember that using the laws of logarithms, this is also equal to the log of the absolute value of secant x plus a constant, because I can bring this negative inside the log as an exponent and take the reciprocal of absolute value cosine x. Well, the reciprocal of absolute value of cosine is just absolute value of sine. So either of these answers is acceptable. Both are correct. They just differ by a basic trig identity. So that trick works in this case if we just have a tangent x by itself. What if we had something a little more complicated? Like what if I had a tangent cubed? Well, if I have a tangent cubed, in this case, what I can do is I can try to break this thing apart in the following way. So I can say, all right, let's take this tangent cubed and let's rewrite it as tangent x times tangent squared x dx. And then what I can do is I can say this is actually the integral of tangent x times 1 minus secant squared x. I'm sorry, 1 minus. Why am I getting so confused here with my signs? I've managed to really screw up my signs. It's secant squared x minus 1 is what it is. My apologies. I'm getting my Pythagorean identities all in a tangle here. There we go. Secant squared x minus 1. That is my tangent squared x. Disregard my ability to write down the negative of that in the first place. So now what I can do is I can say, all right, this is actually the integral of tangent x secant squared x dx minus the integral of tangent x dx. Well, this is now an easy u substitution. I'm going to take u to be tangent x, du is secant squared x dx. So this is going to become the integral of u du. And this integral we just figured out. So this is going to be minus log absolute value of secant x plus a constant. So this becomes u squared over 2 minus log absolute value of secant x plus a constant. And u was actually tangent x, so this is going to be tangent squared x divided by 2 minus log absolute value of secant x plus a constant. And I barely had room to squeeze that in there, but hopefully you guys can still read that. I think that's sort of okay. There is our answer. So what do you do if neither of the substitutions will work? Well, in that case, you got to just kind of be clever about it and try different things and see if they will work, okay? You can try breaking things apart like this and see if you can break it down into simpler integrals. Maybe you can peel something off to where part of the integral can be done with a u substitution. Maybe you got to try doing something by parts. You really just have to try different things and see what will end up working in that particular example. There, unfortunately, and this is the hard thing about integration, there's not always just one specific rule that is going to cover every situation. So you may have to kind of try different things and see, and sometimes what you try won't work the first time, and that's okay. Just keep in mind that if the first thing you try doesn't work, try doing something else. See if something else will work for you. It's sort of like in that old movie Ratatouille, where the chef says that you have to be willing to try things that do not work. That's exactly what it is when you're doing integration. You have to just go into it, try things. Maybe sometimes what you try the first time doesn't seem to work. Well, we go back and we try another method and we see what happens. Now, I want to take a look at another type of integral that actually comes up rather frequently, though this might be perhaps a bit surprising that this comes up super frequently, but it does. What if I want to do the integral of secant x? This one is actually much trickier than tangent, unfortunately, which is why I'm following along on some notes here. And what we want to do here is we want to use the fact that I'm trying to think of how best to explain this in a way that makes sense where people came up with this. What we observe is that the derivative of secant x plus tangent x is equal to secant squared x plus secant x tangent x. So the derivative of tangent is secant squared. The derivative of secant is secant tangent. Well, okay, how in the world is that supposed to help me here? I'm going to take this original integral and I'm going to multiply on the top and the bottom by secant x tangent x. Now, why would I do that? Well, the reason is because if I multiply the top by secant x tangent x, I actually get this expression. I get secant squared plus secant tangent. And if I also multiply the bottom, well then I'm going to be able to use this as a u substitution. So this is going to become secant x times, I wish I had not written this here because I kind of need more space here, but secant x times secant x plus tangent x divided by secant x plus tan x dx. This is then going to be the integral of secant squared x plus secant x tangent x, all divided by secant x plus tangent x dx. Now, again, this is not something that was really obvious to do. The guy who figured this out is kind of famous for it, although I don't remember his name. I think his name was Gregory, but the guy who figured out how to do this, it was quite the accomplishment to think of this the first time. But hopefully you can sort of see where he got to this. And I think he got to this just by kind of playing around with the different things that you can do here. That's really how we make new discoveries in mathematics, by the way. People think of mathematics, they often think of computations. That's not really our main job as mathematicians. Our main job is discovering new results that nobody has found before, not just using known formulas to calculate things. And, well, if you want to find something that nobody's found before, really what you have to do is just play around and see what happens. And most of the time, what you play around with ends up not working out at all. But every once in a while, like that one time in 100, you play around and you get something really, really cool, and it comes out to be a result. Okay, so yeah, I don't know. It would have taken me a really long time to think to do this, but eventually you play around with it and you can think of it, So let's just finish off this problem to see where this is going. We now say, let's let u be equal to secant x plus tangent x. Then du is going to be equal to secant squared x plus secant x tangent x dx. So, coming back up to the top here, we can say this integral is now the integral of du over u. That actually worked out really, really neatly, right? And this is just going to become natural log absolute value of u plus a constant, which is going to be natural log absolute value secant x plus tangent x plus a constant. And there we go. We've managed to work out the antiderivative of secant x. Now, we can now use this to figure out another integral that pops up rather frequently for various reasons, and we'll see sort of where these pop up in the future a bit more, but I want to show you how to do this integral now so that you can see it. Let's suppose that I want to do the integral of secant cubed x dx. This is one where you might try messing around with it sort of like we did tangent cubed. See if we can do some kind of like rewriting in terms of tangents. Well, it doesn't really work out. The problem is I can do it, but I end up with a tangent squared, and there's no way to get a tangent squared out of my u substitution, really. So the approach I used with tangent cubed isn't going to work out. I will leave it to you guys if you want to play around and sort of see what goes wrong with that method in detail. But unfortunately, it doesn't quite work. But here's what does work. I can try doing an integration by parts where I say, let's let I'm going to rewrite this as the integral of secant x times secant squared x dx, okay? And then I'm going to do an integration by parts. And here is my by parts split. I'm going to take u to be equal to secant x, and that means that my du is going to be secant squared x dx. Now, this makes my, hold on a second. Give me one moment to check. There we go. This should be dv, not du. I was like, wait a second, this is not what I want. But it's because I read a u in my notes as a v, and it kind of screwed me up there. So this is why I should probably just stick to trying to do the problems rather than trying to read my notes. But I wanted to check my notes because these are complicated enough that it's easy to get lost. Well, when you do this, then your du is going to become secant x tangent x dx, and v is going to just be tangent x, because remember, we know the derivative of tangent is secant squared, so we can go back from dv to v fairly easily here. And then that means I can rewrite my original integral as u times v, so this is secant x tangent x, minus the integral of v du. So this is going to be tangent squared x times secant x dx. Now, so far, this doesn't necessarily seem like it's that great. However, we can, in fact, go ahead and rewrite this one in the following way. And like I said, this is a rather complicated problem, so there's a reason why I'm keeping my notes with me on this. I can rewrite the tangent squared as secant squared minus 1. Remember, we've done that multiple times today, where we've taken a secant squared and rewritten it as secant squared minus 1. Okay, well, how does that help me? I need my eraser because I need some extra space up here. I'm going to leave this for now, and we'll see why in a second. So I can rewrite and say secant cubed x dx. This is now equal to secant x tangent x minus the integral of secant cubed x dx plus the integral of secant x dx. So, we just saw how to do this integral, right? It's the natural log of absolute value secant x plus tangent x. And I can add the integral of secant cubed x dx to both sides. So I turn this into 2 times the integral of secant cubed x dx is equal to secant x tangent x plus the integral of secant x dx. And this is going to become secant x tangent x plus natural log absolute value secant x plus tangent x plus a constant. So finally, what I can do is I can divide both sides of this by 2, and I get my answer. We end up with the integral of secant cubed x dx is equal to 1/2 times secant x tangent x plus natural log absolute value secant x plus tangent x plus a constant. Whew. Okay, so that was quite the problem there. That was a rather challenging thing to work out. And again, this is one of those things where, like, somebody had to think of this the first time. That was quite the accomplishment. Now we can kind of follow what they did, and we can check each step makes sense, but like coming up with each of these steps, well, you just kind of have to play around with what's going on. And this kind of playing around with the different steps that you want to take, you often will end up going down sort of the wrong road the first time, but you just go back and try something else and see what happens. So in this case, we ended up having to do integration by parts and then split the remaining integral and then we end up with the original integral written in terms of the original integral, but that allows us to then solve for the original integral this way. We've done a problem like this in an example before, it just wasn't quite this involved. Now, I want to note here that you can do the same kinds of tricks with cosecant and cotangent. Okay, so the cosecants and the cotangents, they work similarly to the secants and the tangents. And the reason is because, well, they follow a similar pattern with their derivatives, and they follow a similar pattern with the Pythagorean identities. So I will leave it to you to look in the books and in the notes to see, yeah, the cosecants and the cotangents, they work pretty much the same way. All right, so I do want to do just one more example here to show you how this kind of thing can sometimes come out a bit differently. So, or how you can use these ideas, I should say, to kind of think through other types of problems. So here is the way that the problem that I want to think about. Let me suppose that I want to do the integral of tangent to the fourth x sine cubed x dx. This is a bit different than what we've done before. But how can I go about using the ideas that we've said so far to simplify this into a form that I can actually work in? Well, I'm going to rewrite this, first of all, because I've got this sine involved. I want to see what I can do in terms of sines and cosines. And I notice that this is actually the integral of sine to the seventh x divided by cosine to the fourth x dx. Now, this is suggestive because I have an odd power of sine. And if I have an odd power of sine here, then I can peel off one of the sines and think of this as the integral of sine to the sixth x over cosine to the fourth x times sine x dx. There we go. And the reason this is good is because I'm left with an even power of sine. Well, I can turn even powers of sine into cosines. In fact, this is now the integral of 1 minus cosine squared x cubed divided by cosine to the fourth x sine x dx. Now, do you see a u substitution that we could make here? Hopefully you're able to notice that at this point I can take u to be equal to cosine x, and then du is negative sine x dx. Therefore, this becomes the integral of negative 1 minus u squared cubed divided by u to the fourth du. And now this is just a basic, well, it's not basic, but we can turn this into a basic, like, it's almost like a polynomial. It's not quite a polynomial, but it's somewhat similar to a polynomial. So I'm going to leave working out the final details of this to you guys as a little exercise. If you run into trouble, let me know, and I'll be happy to help you out with that. But just expand this out. Use the binomial theorem or just multiply it by hand. So expand this out, divide all of the terms by u to the fourth, and then do those antiderivatives, see what you get. And each one of those should be relatively easy, and then you replace all of your u's with cosine x's, and you're done. So you can use these kinds of ideas that we've had from the types of integrals we've looked at to try to solve other types of integrals as well. All right, now because this is such a challenging topic, because doing these trig integrals is really, it's not easy. There's a lot of stuff going on here. So I've posted some extra resources to worked out problems that you can look at, and make sure to take a look at those postings because they will show you a bunch of worked out examples, and just seeing these examples helps you see the different tricks that will work in different situations. And if you run into any questions with those, then let me know. Also, of course, read the examples in your book, but I wanted to make sure you guys have more examples than just the examples in your book. All right, next week we're going to start seeing how you can use these types of things to do what's called trigonometric substitutions, where sometimes they're called inverse substitutions, because essentially what we do is we start with something that just involves like a regular expressions involving our variables. We turn it into something involving trig functions, and the reason we do that is because we can then use trig identities and trig integrals to solve those problems. So that's what we're going to start working on next week.